Okay, so we have discussed regarding angular acceleration, angular displacement, and angular velocity. But now we're trying to find the relationship between all those three: angular, displacement, velocity, acceleration, and the actual displacement, velocity, and acceleration of a point on a rotating or rotating point on a rotating body. For example, let's say we have a point P, and this point P is experiencing a rotation because the rigid body, is experiencing a rotation. So this point P we can define using a, well, you can define it as you have a radius here, right? So you can also define the position of this P by the position vector of R, which extends from the center of the rotation to the point P. So if you do that, if the body rotates by d theta, so a little bit of change of angle, it will be displacing amount by amount of ds, the displacement of P from one point to another point. The ds is equal to the value of r times the value of the angular displacement d theta. So finding the velocity of P can be done by actually you do derivation, but you can divide what the equation that we have just now, ds equal to r d theta. If you divide by dt on both sides, so here you already know this is v, and here you already know this is omega. So v is equal to r omega, and the direction of the v here is tangent to the circular path here. So it is actually tangential velocity, which is, well, quite similar to what we've discussed in chapter 2, right? So the magnitude and direction of v, you can find using the cross product of omega and your r here. So let's say rp is directed from any point on the axis of rotation to point P. So this is your axis of rotation, and then you have a vector pointing to a point P. So the direction of v is established by finding the cross product of the direction of the velocity, angular velocity, and the direction of the vector rp. So you can find the value of v. So let's say that the your r here, lies exactly on the same plane with the motion of plane P, meaning it is on the same, like it's a paper, it's on the same plane. So you can simplify rp into just the r, which is the radius from 0 to the point P. So you can find the cross product of omega to r. So what is actually the direction of v? So finding the cross product of the angular velocity and the position vector. So what is the cross product of omega and r? And remember, cross product, you cannot just change as you like, meaning this is not the same as r times omega. So please remember this. So if omega times r is omega times r, it cannot be r times omega. Why? Because to find the direction of v, you need to use the right hand rule. The right hand rule of direction of omega to r. The direction of omega is in this direction, right? It's the axis of rotation. R is in this direction. So using right hand rule, from omega to R, so meaning from omega to R. So it is in this direction. So using your right hand rule, your four fingers, you point this in this direction. So where will your thumb be pointing to? Your thumb will be pointing to this direction, right? So meaning the direction of V is actually tangential, which is correct, like what we did before. So what about the acceleration? So the acceleration of P, and as we've discussed also in chapter 2, you can express the acceleration into two, which is the normal and the tangential component, where remember at is equal to dvdt, right, and an is equal to v to the power of 2 divided by rho, where if this is a perfect circle, the rho is actually the radius, right? So actually for angular values, it is the same, because we already know v is equal to, I'm sorry, not v, a is equal to alpha times the radius, right? And a is equal to dvdt times r. So you can just multiply your angular acceleration with r to get your tangential acceleration. To get your normal acceleration, you need to multiply to omega to the power of 2 of 2r. Why? This is because, as discussed in chapter 2, an is equal to v to the power of 2 divided by rho. And in this case, and also before this, we know that v is equal to omega r. So omega r to the power of 2 divided by rho. So rho is r, because this is a perfect circle. And omega to the power of 2 r to the power of 2 divided by r means it is omega to the power of 2 times r. So this is just the rearranging. It's not really complicated. So this is how you convert from your angular components to your acceleration and velocity. So what does it mean actually, your tangential component of acceleration and your normal component of acceleration? Well, actually the tangential component of acceleration, or AT, represents the time rate of change in your magnitude. Meaning if your P, the speed of it is increasing, then AT will act in the same direction as your V. If the speed is decreasing, meaning you have a deceleration, AT will be acting in the opposite direction of V. If V is constant, then the value of AT will be 0. So it represents your change in magnitude for your velocity. And what about the normal component of acceleration, or AN? So AN here represents the rate of change in the velocity direction, which is why it have a relationship with your radius. And the direction of AN will always be towards O, which is the center of your rotation. So knowing the AT and knowing the AN, how do you get the value of A? well, actually not the value but the direction of A. So to find the direction of A, we need to find the derivative of that is what we get before this, right? The velocity vector is equal to the cross product of the angular velocity times the rp. So finding the derivative of this, you will get the derivative of the omega times rp plus omega times the derivative of rp with time. So solving for this, you know what is this? This is angular acceleration. And what is this? Because the change, this is actually a double derivative. Right, we have a small rp. Oh wait, I'm sorry. The rp dt, what is it actually? This is the rate of change of your position vector to time, which is actually the velocity, right? And you already know what is the velocity. It is equal to omega times rp, the cross product. So you put this inside, so it becomes here, and here is acceleration, angular acceleration. So it becomes A is equal to angular acceleration, cross product of angular acceleration and rp, plus angular velocity times omega times rp. So how do you find the direction? So for the first term, the omega times rp, what do you get? So to find the direction of your an and your, the direction of your acceleration, so you need to see here that you can divide this into two. So the first term, the cross product of the angular acceleration with the rp, with your position vector. If you find using the right hand rule, immediately you will know. So remember the direction of acceleration is same as the direction of your axis of rotation. So finding this cross product, you will know that using your right hand rule, you will get actually the direction of AT here, which is tangential. So the second term, here you need to do your right hand rule twice, one for this 2, and then omega n whatever you have here. So doing this first, what will you get? So same, the direction of omega is the same as the axis of rotation. Finding the cross product with rp, what will you get? You get actually the vp. Where is vp? It should be in the also in the tangential direction. You have your vp here. So next you need to find the cross product between omega and vp. So finding the cross product between this direction and this direction will get you, so let's say this is vp. So finding the right hand rule, you should get that the direction will be like this, right? Which is actually same direction to negative r. So r is in this direction, right? R is in this direction, but the cross product of omega with vp will be in the opposite direction of r. which is actually the same direction with AN. So meaning, you can simplify this. A is equal to AT plus AN. So AT is equal to the angular acceleration, the cross product of angular acceleration and the position vector. And because you have the same AN have the same direction with negative R, so finding the value of AN, it should be negative omega to the power of 2 R, because as you know, we got just now, AN, the magnitude is AN equal omega to the power of 2 R, but the direction, if you write in vector form, AN is equal to negative omega to the power of 2 R. So this is how you find the direction of the vector, and actually you will get something like this lah. ATAN, direction should be heading inside here. So this is the direction of your acceleration vector. And if you want to find the magnitude of A, of course you can just find using this formula lah. AN to the power of 2 plus AT to the power of 2, you get the square root.